From the University of Glasgow.
Thank you very much for the introduction, and thank you everyone for coming to my talk. So today I'm going to be talking about some joint work with Duncan Attard, Franciszek Sowul, Simon Gay and Phil Trinder about how we can use mailbox types to help us assure the safety of actor-style languages. So communication and concurrency is difficult. Right, so we can very, very quickly get into hot water as soon as we have more than one thing running at once. And to help tame this complexity, we've got a class of languages called communication-centric programming languages. These are things like Erlang, things like Go, things like Elixir. And these really put communication and concurrency at the heart of their design. Here we have isolated threads which communicate using explicit message passing. And really, this allows us to avoid many of the pitfalls of shared memory. For example, we don't need to worry about the order in which we acquire a lock, for example. But they're most certainly not a panacea. So we can drill a bit further down into the different classes of communication-centric language. We've got channel-based languages. These are things like Go. And here we have anonymous processes which communicate over channels. These can be buffers, for example. And here we have ordered and bidirectional communication. And in fact, these things are very easy to give types to. So in Go, we can have a channel where we can send and receive things of type int, for example. And actually, we can have much more fine-grained type systems for channel-based languages, things like session types, where we can say, okay, well, I want to go and send two integers, receive a bool, and then end. The kind of not so nice thing about channel languages is that they don't have such a nice distribution story. And, you know, actor-based languages, things like Erlang and Elixir, have had real success in developing reliable distributed systems. So here we have a different communication model where we've got named processes, and each of them are associated with an incoming message queue known as a mailbox. Here we have unidirectional and possibly unordered communication because we can potentially pick something out of the mailbox. And this makes things a lot easier to distribute, but a lot more difficult to type. So just to start with an example here, I'm going to start with an example of a future, right? And this is typically a placeholder variable where we can write to it once and read from it many times. If we have multiple writes, then we get an error. So we'll start off with the empty future, and what this function does is we wait for a put message, and when we get that put message, along with some value x, then we transition to the full future state. Now, note that we can receive get messages in this point, but we don't process them yet. Then, when we're in the full future state, at this point, we can start processing these get messages, right? And when we get a get message, we get back a process ID to which we send the reply, and then we recursively then go and process the remainder of the get messages. If we get another put message, then this is an error, and we need to go and flag this at runtime. The main function ties everything together, so we spawn a future, we send it a put message, then we send it a get message along with our own process ID, and then we receive the result and print it out. And here I'm saying that we're printing out the result plus 10. Now, this is a fairly small program, but we can still get it wrong in a lot of different ways. So the first thing that we can do is we can just violate the protocol and send two put messages. And at this point, what we would get is we'd get that multiple writes error manifesting itself at runtime. We could also not send a put message at all. And at this point, the future will be waiting forever. Now, we could then forget to send a reply message in that get clause there. And at this point, even though we've made the request will never be fulfilled, and we hang forever in the client. And another thing that we can do is potentially have an unexpected message. So here's surprise. And this might seem innocuous, but if this is in a tight loop, for example, we could soon get a memory leak, for example. Another thing that we could do is have a payload mismatch. So here we're sending a put message with type hello, but when we actually receive this response, we're having a result plus 10. So we're trying to add 10 to a string. the list goes on, actually. So we can also do a self-deadlock. So here what we're trying to do is we're trying to get the reply before we've actually sent the request. And of course, here we'd wait forever as well. So small program, lots of ways it could go wrong. So this kind of actor-style communication has been looked at in terms of a type system in the past by Ugo de Ligero and Luca Padovani. They published a lovely paper at ICFP' 2018. And the idea here is to type a mailbox with a mailbox type. Now, each mailbox can have many send references, so many different processes can send to a mailbox, but it must have only one receive name. So the goal, really, of this type system is for the sends and receives to balance out. So let's have a look at the patterns which form a commutative regular expression. The first is an atom, so this is a message with tag M. This is something like put or get. We've got conjunction, so this is patterns E and F, and since this is a commutative regular expression, this is the same as saying F and E. We've then got disjunction, so this is pattern E or F. We've got replication, so 0 or more copies of E. The empty mailbox, which contains no messages, and finally, the unreliable mailbox. Now, a user will never write this, but this is used for type checking to show that something's gone wrong. And now we can give some examples from our future program earlier. So to start off with, the future will have the empty future type, and this is a receive mailbox type where the mailbox can contain a put message and many get messages. We've got the full future, which can receive many get messages, but explicitly no put message. We can have a client send, which is the obligation to send a reply message. And finally, the client receive, which is a receive capability saying that the mailbox contains a single reply message. Now, de Ligero and Padovani worked in the setting of a process calculus. Now, process calculi really distill down the essence of concurrent communication. Here we have things like parallel composition. We've got things like name restrictions, which bind, say, the name future within that particular scope. But they don't look like a programming language. We wouldn't want to write anything like that. And essentially, this is because a process calculus shows a snapshot of a concurrent system, whereas we want a programming language which must be able to describe the program a user writes in something like Vim. So just to skip forward a bit, we've developed a programming language for the mailbox calculus. And we call this Pat, after the kids' TV show in the UK called Postman Pat. And essentially it looks like this, and it looks a lot like the Erlang code that we saw earlier. Okay, so I'm now going to go and show you a demo of the tool that we've done. So what we've got here is the future example from earlier. It's essentially pretty much a transcription of the core calculus that I showed. And if we now do mb check future.pat, at this point we can see that evaluated successfully. So now we can start doing multiple puts, for example. We can start screwing things up. And here what we have is we've got the inferred type put.put.get, which is not supported by the annotation that we've got up here saying put.starget. We could delete the put altogether. And again, get is not supported by put.get. We could, let's mess this up and do hello in the payload, at which point we've got type mismatch. Right, let's do, should we do the self-deadlock? Right, so we'll put that there. We do that and return 5. And we need a semicolon there as well. That's the first time I've actually managed to get that proper error the first time. And that, again, is now saying that mailbox variable self was used after being consumed by a guard or a let binding. Okay, so all of those errors that we saw earlier, we can actually now rule out statically using this system. Now, I want to get on to, firstly, why it's hard, and then how we did it. So the first big challenge is this distinction between static and dynamic. In a process calculus, we kind of know the names a priori. We can write down new future, for example, and new self. And they used this to good effect in the original Mailbox calculus paper in order to have a graph-based approach to alias control. Now, in a programming language, we can't do that. We need terms like new, which at runtime then evaluate to a fresh name. And then on top of that, we've got things like sequential composition. How do we handle that? How do we handle things like variable rebinding and aliases? And kind of more specifically, we get lots of name hygiene problems. So here what we have is a use after free bug. Really what we want is when we guard on this mailbox, we want to use up that X and then rebind it in the receive clause and not have access to it in the free. However, we can quite straightforwardly, in fact, do some programs, if we do this naively, where we can actually use that X after freeing. So this is easy to do with a linear type system, but we can't use a linear type system here because we need multiple references to the same mailbox in order to send to it multiple times. Now you might think, well, couldn't you just make sure that what you're guarding on, the variables that you're guarding on, don't then occur in the body of the guard? And that works, and that rules out the problem here. But we can quite straightforwardly then circumvent that using things like variable renaming and things like evaluation contexts. And then we also need to remember that this is a concurrent language, so we might end up introducing aliasing via communication. So the way that we get around this is by making use of something known as quasi-linear typing. So quasi-linear typing was introduced by Kobayashi in the 90s. The formulation that we use is closer to a paper by Ennell, Sharp, and Mycroft a bit later on. And the idea here is that we can use each reference once per process as a kind of full reference, but many times as what's known as a second-class reference. So the full reference, or the returnable reference, these are things that we can let bind, and we can return them as part of an expression, and we can guard upon them, whereas a second-class reference can't be guarded upon, and it can't escape its scope. Then what we can do is we can enforce an ordering constraint, which means that the returnable reference must be the last occurrence of the name in a particular thread. So just to give you some examples, here is our client example from earlier, and we want to see how this works with the self reference here. So we start by sending it to the future as a payload to the get message, and that we can do as a second-class reference. Then we guard upon it, which needs to be returnable. Sorry, I should have said that the little white circle is a second-class reference and the full circle is a first-class reference. Then what we can do is we can rebind it in the receive clause, so that self is a binding occurrence, and then we can free it. Now, if we then try and do the same thing with our use after free example, we can quickly rule this out, right? Because we're guarding on something. So here we've got receive message and we've got the full reference, and then we have these two occurrences down here which are only second class. So this all works, the mailbox typing works out because what we want to do is we want to go and cancel the sends and receives. So if we have two sends, then what we have is a send E and F. And when we're combining a send and a receive, what we do is we have, well, if we're combining send E and then receive E and F, then what we get back is something which allows us to receive F, and that's a commutative operation. So there are many different ways that we can write semantically equivalent mailbox types, but essentially what we do, the core technical thing that we use is subtyping to rewrite semantically equivalent forms where we can apply these two rules. We also have combinations for usages, so we can combine the two second-class usages or a second-class and a returnable usage, but note that this is not commutative and we can't combine two returnable types. And to see how this is used, here's our let rule. I've got a type annotation here. It's optional. You don't need it in the actual tool, for example. And what we're doing is we're checking that the subject of the let has a returnable type. And then we've got this sequencing of these two environments, which ensures that the mailbox types combine correctly and have these same quasi-linear well-formedness properties. So I'll just tell you about an example derivation here. So here's a very, very simple program. And what we're doing is we're creating a new mailbox, we're sending M, then we're receiving M and freeing it. And let's do a derivation here. So to type a send, we need a type context where we've got X of type send M. Then in order to type the receive guard, we need something of type receive M with a little circle. And then combining those two things together, we get something which is now the empty mailbox. We can put that in the context of the overall expression. So new has type receive empty mailbox. And then we can eliminate that using the let, and it's typable under the empty context. So we've got nice meta theory here. We've also, so we've got preservation, which says that if gamma is reliable, so doesn't contain anything with the unreliable mailbox in it, it's well typed and it takes a step, then the reduct is also well typed. And as a corollary of this, we have that we will never get into a situation where we've received something that we shouldn't have done. And this is really hard. We needed a frame stat representation, and it requires quite extensive reasoning about context and quasi-linearity. The next thing that we have is an algorithmic type system, right? So that's a declarative type system. It's nice to reason about, but we can't implement it as is. And this is because essentially we've got this, if we're reading things bottom up, we've got this non-deterministic environment splitting, and we've also got to reason about environment subtyping in order to go and see what things we can combine. And that boils down to a load of pattern inclusion problems. So instead of doing the usual way of writing a type checker, what we do is take what's known as a co-contextual approach. Now, co-contextual typing was introduced in 2015, I think, at UPSLA. It's a lovely approach, and the idea is what we do is we produce a type environment and a set of pattern inclusion constraints as an output of our type checking algorithm rather than an input. Now, we use a bidirectional approach. So the standard bidirectional typing approach has two judgments. The first is a synthesis judgment, and here we say that under type environment gamma, we can synthesize type A for term M. And the second judgment says that under environment gamma, we can check that term M has got type A. Now, the backwards bidirectional spin on this allows us to do the following. So this was an idea of Noam Zarberger in 2015, and I learnt about it by the lovely bidirectional typing survey paper by Jana Dunfield and Neil Krishnaswamy. And essentially what we have here is we've got that term M can synthesize to type tau, producing environment theta and pattern constraints phi. And we've got a checking judgment which says that we can check that term M has got type tau and produce, again, environments theta and pattern inclusion constraints phi. And the idea is we want to go and stay in checking mode as long as we possibly can, because at the point we get to the variable rule, what we can do is we can construct a singleton environment saying that X has got type tau. And then as we go down the tree, we can merge things together. And just to kind of see how this works with the let rule, what we want to do is, if we're type checking let X equals M in N, we want to go and firstly go and check the body, and that then allows us to inspect the produced type environment, allowing us to deduce that X has got type tau. We need to go and check that tau is returnable. And then we can use that knowledge to deduce what we need to check M as to get the output environment there. Then we combine the two environments, and then what we have is the entire let construct being typed. So we've got some meta theory here as well. So we've got algorithmic soundness, which is essentially don't accept nonsensical terms. So if a type is, if term is typable in the algorithmic system, then it's typable in the declarative system. We've got algorithmic completeness, which says that we don't reject sensible terms. So if a term is typable in the declarative system, then it's checkable, not synthesizable, checkable in the algorithmic system. Okay, so we have implemented this, and we use a fairly standard pipeline. We have our parsing and lexing and desugaring. Then we have a conversion to an explicitly sequenced intermediate representation. We've got some typing steps followed by constraint generation. Then we get to the constraint solving stage, and at this point we apply a known closed form solution to the pattern inclusions before shipping things off to the Z3 solver, just to make sure that everything's consistent. We've evaluated this against a factory use case, which was done in collaboration with our industry partner Actix. And this is basically working with modeling robots on a factory floor. So the idea is that there's a single warehouse, and we don't want more than robots in there at once, more than one robot in there at once, sorry. And this is actually quite tricky to do with most session type systems. I mean, it can be done in some, I'm sure, but it's a lot more natural to do it in this kind of setting. And we end up with a programming style similar to something known as akka typed, which is a simply typed way of doing things in akka. We've also done a selection of the benchmarks from Savina. Here we can see all of these, and we can see that they're actually all type checkable in under 100 milliseconds, so that there aren't any obvious scalability problems. Same with the factory study as well. And we can also encode all of the examples from the original Mailbox calculus paper, even though we don't have the same fine-grained alias control that they have. Okay, so just to wrap up now. Mailbox types allow us to type the mailbox rather than the process. And today I've talked about the first integration of mailbox types into a programming language. And to do this, we really need quasi-linear typing to handle the many-writer, single-reader pattern. We've then gone on to do a sound and complete algorithmic type system based on backwards bidirectional typing as well. And there's lots and lots to do in future. So we've started doing some work on how to compile first-class mailboxes into actor systems. It'd be nice to look at a more to go from the bidirectional setting and have something where we've got more type constraints, for example. Some more sophisticated alias analyses. We're currently pushing really hard on tool integration, in particular with Erlang and Elixir. And I think that this can also be used to get language integrations for behavioural type systems for other many-writer communication paradigms, things like publish, subscribe, or type state. That's it. Thank you very much for your attention.
Thank you. Thank you, Simon. Any questions? If you could say your name and affiliation.
Yeah. Okay, I'm Giuseppe Castagna from IRIF, Paris. Thank you for the talk. You never spoke about subtyping, and it seems that there is a very natural notion there, which is regular language inclusion. Did you consider it, and would it work?
Okay, so the question is, what about subtyping, basically? Subtyping is actually crucial to this. So there are many different ways of actually writing the same mailbox pattern. And we actually need subtyping in there in order to go and handle things like inclusion of a single atom in one which says that we've got many, for example. So it's actually critical. And the way that it works is that we give a semantics to the commutative regular expressions, which gives us a set of multisets. And at that point, we can do just regular set inclusion to determine subtyping. It's contravariant in send mailbox types and covariant in receives.
Thank you.
Thanks.
Any more questions? You've got a nice wee language you made yourself, but would it be possible to code up some aspect of this, like a DSL in Haskell, using the linear type extensions in Haskell, STM for do you have enough in Haskell to be able to cobble something up?
That's a lovely question. If I'm understanding right, it's this is a standalone language. Can we do it with existing tools? Haskell being an example because it's got a very rich ecosystem.
Yeah.
I would love to try this in particularly Cloud Haskell actually, because Cloud Haskell's got a very similar thing where we split out essentially a mailbox into something that can't be sent, and we can then send many things to it. I haven't tried it. I've had the same thought though, and I think it's a lovely idea, and I think it'd be really interesting to do.
Any more questions? If not, then we can wrap up a few minutes. A few minutes. So shall we do that? Is that the best plan? We should wait till 5 minutes for the next one. Okay, that's good. Thank you very much, Simon.
Thanks very much.